Okay, welcome everyone to What's a Microcontroller with Python and the Microbit Workshop Day 3. Thanks for coming back, everyone. My first question for all of you is, how did the homework go? Okay, so Chris gave me 2 thumbs up and Elaine has gotten partway into it. Oh, looking good. I see that's definitely the Ohmmeter circuit. Unmute, Chris.
Yeah, it went pretty well. The only thing, I didn't quite get the readings that I was anticipating. So we'll talk about that when we start playing with it, I guess.
Yes, let's talk about that. Okay, yeah, I'll try to do that along with you and we'll see how it goes and if there's possibly an error somewhere or, well, we'll do that momentarily. Just a quick first off. So today we'll do homework discussion and then a few more servo apps, a few more potentiometer apps from, beyond the homework. We'll talk about planned activities and projects. I'd really like to get some teacher feedback on, which ones are going to be important and which ones, basically just kind of some triaging information. I'll share some purchasing tips with you. We'll revisit the student resources and then I'll take you through the teaching materials. There's also some cyber.org curricula to show you. And then there's some fun MicroPython related kits with the Microbit, primarily the Cyberbot robot. It's a lot of fun. So I'll show you some of its features. And then that'll round up the workshop. So are you guys ready to get started with a homework review? On my way there right now. Oh, actually, so for review on the homework, so this is the potentiometer. It's essentially, if you only use 2 of the pins, either W and B or W and A, it's essentially a variable resistor where you can turn this adjustment knob to change its resistance. If instead you use all 3 terminals, it's something called a resistor divider, which in and of itself isn't very exciting until you start connecting voltage to A and B, because then you can see an adjustable voltage at W, and that's actually how the joysticks in game controllers work. And that's a pretty neat thing. So this homework was primarily something I did because potentiometers are often reduced to a paragraph and a couple of pictures. And I don't think everybody who tries tutorials, whether they're ours or elsewhere, really understands a potentiometer. And so what my hope was for this was for the students to really get a gut level sense of how a potentiometer really works. Okay, so I'm in a Mac instead of a Windows machine today. I can't remember the keyboard shortcut for zooming, so here we go. So in the homework, we collected the potentiometer, then we added the Ohmmeter circuit right here. And so this shows both the Ohmmeter circuit and the potentiometer. And what we're doing here is we have one probe on the B terminal. This is the A terminal, B terminal, and W terminal. And then we have another probe on the W terminal. And so measuring resistance with the Ohmmeter should give us some value between 0 ohms and 10 kilo ohms as you twist the adjustment knob. So step 1, download Ohmmeter Cyberscope .hex. I'll go ahead and, well, I did that wrong, didn't I? Let's try Okay. This is at learn.parallax.com. Copy link. All right, I'm going to have to, I might need to find ohmmeter.parallax.com elsewhere. Let's see here. Okay, bear with me a second. So in What's a Microcontroller, I believe we use ohmmeter in electrical measurements, measure resistance, script and tests. Okay, so this is Ohmmeter Cyberscope. Save link as.
I will update that link to
Downloads.
right.
Yeah, I was going to chat everybody in just a second. Copy. But if you can get the chat before then. Okay, I'm in. Paste. Whoa. That's right. Okay, so this is where to download Ohmmeter Cyberscope .hex.
Remember to right click it.
Yes, remember to right click and select Save Link As. Okay, then we're going to go to python.microbit.org, which I will also paste in. There you are. And then the next step is to drag and drop the hex file you downloaded into your Python editor. And then connect, flash, disconnect, connect, flash. And before I disconnect, I'm just going to show you quickly this is what the actual data that's being sent to the Cyberscope looks like. It's actually just a string of characters that is indicating right now that resistance is 6904 ohms, and then there's a timestamp on it. But that was just for your information. Typically, we just disconnect and then go to cyberscope.parallax.com.
Now, you had us change the sleep amount on it.
Ah, yes, you are paying better attention than me. Let me do that. So it was sleep 200, yes? Flash. Disconnect. Then move on over to Cyberscope, hit connect, select your microbit. And so there we are with the resistance measurement. Now, I'm a little bit behind you guys because I forgot to connect my probes as shown in the picture. So I'm catching up on that right now. And let's see after I do that, how it looks. Just about ready. Oh, and then I've got to make sure to remove the wires that I have connected to it currently, because I had it a little bit ahead for today's workshop. Okay, so after connecting all these wires and then turning the potentiometer, I'm not seeing any response. Now, is that what happened for you, Chris?
No, I get when it's turned all the way one way, I get 9,300. And
Okay.
The other way, it goes all the way down to 8. So
perfect. Yeah,
it's probably within the range of the plus or minus 5%.
it is. Well, it's definitely in an acceptable range, and I'm not even sure that the potentiometer is a plus or minus 5% device. I'm thinking that it may have a more significant margin of error. It might be a 10 or 20% device.
Oh, okay. That makes sense then.
Yeah, because yeah, down an entire kilo ohm makes me think we might be a 10 or 20% device. Okay, and incidentally, the reason that it's not working for me is because I had to switch computers just before the workshop started, and so I forgot to disconnect the microbit from my Windows machine and connect it to my Mac. So here we go. Disconnect, Cyberscope, connect. All right, so that looks a lot more alive. Okay, so for me, I'm 200 ohms, 300, 400-ish over. Wow, I actually got an 11 kilo ohm reading. And then all the way down at the bottom, mine goes down to the teens to tens. I just let go of it. If I bring it back, there we go, 80 ohms. It's jumping around a little bit, but overall, that's definitely good enough. And I tried to put some info in there saying, hey, it can be off by a ways. I don't remember actually exactly what I said. Because we may want to make a slight adjustment here. I think I said, oh, look at this. So I was talking 9.5 to 10.5. And Chris, you're saying that your measurement was actually closer to 9.0 on the all the way clockwise.
Yeah, it was about 9.3.
Okay.
Quite a bit, but it stayed at 9.3. That's why I thought it was a little bit out of range. But
yeah.
it's nothing compared to what you've got.
There.
Which page are you on for that in the tutorial?
Stephanie, I will go ahead and paste that in. Let me make sure I know where I am. I believe I'm in the tests part. Okay, so that is tests right here.
Oh.
Copy.
Okay, I will go fix that right now.
I already did.
I mean, in the Learn site.
It's not in the Learn site yet.
Well, then I can't fix it there yet, can I?
No.
Okay. I look forward to posting this tutorial though.
It's coming soon. This is the draft version of the tutorial, by the way. So that's why you ended up in a Google Doc as opposed to learn.parallax.com. And I wanted you to try out this particular lesson simply because it seemed like something new and that folks haven't been offered before, just to kind of get some opinions on, you know, one, is it too hard? Well, one, does it work? Two, is it too hard? And three, what if anything would you want to change about it? So if anybody would like to offer opinions, please let me know, because we're doing this for you. Yes, Mark.
Okay, so I feel like the content is perfect, but instead of using bullets, to maybe break it up into smaller pages, because what I know that I'll do when I use a lesson like this is I'll probably have to copy and paste it myself. So maybe if you can put it into some like smaller components that are numbered, it would work a lot better for I know like senior students could probably handle it, but like freshmen and sophomores, that enumeration is very, very helpful. But in terms of the actual activity itself, I mean, I feel like the graphics are superb. Everything that you're showing, the diagrams are fantastic. And I actually missed that with the 3 legs on the potentiometer when I looked at it on the homework. That's like such a cool feature. And what I really think is strong too is how you make that connection to video games. anytime we can brainwash these kids into doing work while talking about video games, I think is a really good idea. So
Well,
I
talking
really
about
like-
video games, playing with robots, yeah, really
but
got
you know,
it.
like talking about the joysticks or game pads,
Yes.
like that is such a strong motivator for a lot of these children. So I really like that. And like I said, if you can just, I mean, I'll do it on my own as I go through and do this sort of stuff, but
Yeah.
to break it up into the chunks might help a little bit. Because on the left-hand side, how you have that panel,
Okay,
like
just a
that's
second.
perfect. Just maybe like a sub.
Oh, this
yeah,
thing.
Yeah, that's perfect.
Yeah,
But-
that's really nice. Yeah, so what we do, if we were to go to a more standard, so here is, for example, one that is actually published. And we use the, we've been using the little red check marks simply because it reduced the intimidation level. And so the other thing is that we, because electronics especially has a certain amount of intimidation. And so the check marks are there for students who may be a little bit distractible, to highlight, look, if you're going to skip reading anything, at least read these, because these are the steps you have to follow. So even if you didn't read any of the theory, don't
which is
skip
hard
the
for them,
steps.
you know, like, which is really hard for them. They will do anything they can to skip the theory.
Yes, and this is actually one of the reasons we've been working on this format for a while. Not to say that it's necessarily set in stone. That's one of the reasons we really like deploying it over the web, is that with an activity. So here's a chapter, electrical measurements. And so we talk about what it's about, and whenever possible, try to get in a plug for the real world. And in this particular case, since it's pretty technical stuff, I'm still in the electrical measurements chapter. It's hard to find an example of video games or robots necessarily, but with measure resistance, so we set it up so that we have the main topic, an overview of what you're going to be doing, and then we talk about parts and circuits. And so here are the parts, and then here is the circuit. And so in addition to the GIF, we have the step-by-step check mark instructions to draw their attention that these are action items. Then we have our script and tests. So here's the script, and then these are the steps that the student will follow when they're doing the test. So in the draft, we don't actually have the luxury of it. So Stephanie, when she's
That's my fault then, because I didn't realize. I thought that this was just a different area. No, I really like the other ones. I didn't realize that this was not part of the
yes, and I didn't explain that. I apologize for that. This is the way our drafts look.
Okay.
We do them in Google Docs, and then as Stephanie is flowing this to the web and correcting the author's numerous errors, she also does things like add the red check mark. Additionally, the way I have it is a little bit more granularly split up. You know, I've got parts as a section, circuit as a section, script as a section, but over here, the way it ends up is that there's script and tests, and then how it works has a try this below it. So something for the students to do. Then there's a did you know, which in this case is series versus parallel resistance. And at the end of the did you know, I hope it is, I'm beginning to doubt it's going to be, oh yeah, there is a your turn. So we've got them doing the calculations here. So they're putting their hands, in this case, on a calculator keyboard. And so, so we have combined how it works with try this, and then did you know with your turn. But in the draft, it's actually all broken out, and that's mostly to help
See,
me write
that's
it.
what I was confused about, because the web interface was absolutely fine. And again, it's in, decent chunks that, if I copy and paste into Google Classroom, and blast that out to students, that they'd be able to follow it. So
Oh,
I guess
fantastic.
that was
Okay.
my misunderstanding, that was just the draft. So I apologize. That's not what I was trying to get at. It just, in terms providing feedback, like in terms of the website though, when I went through the tutorials for the homework, I didn't have any problem with that. It was just when we were looking at that one particular thing, and that I didn't mean to.
Well,
hijack
but
the
it is
conversation.
interesting because there has been discussions internally of enumerated versus checklist instructions for many years. so that is a thing. And so hearing that from you is just, it kind of keeps it on our radar. And we do go to that format when we have to refer back to something. So normally all of these are just, you're doing it here and then you're going to the next step. But if there's something where there's actually a test where it says, go back to step 2, then we will switch over to enumerated, but it'll be enumerated under a check mark that says, do all those enumerated steps below. And I don't know if we actually have one of those, but that is the way we would almost certainly approach it if it came up that way. If it was an iterative kind of test.
That makes sense. Or to have them be unchecked check boxes that would be interactive, and as a student follows along.
Yeah.
I'm sure you've had these fights even down in the, I don't want to get down in the weeds. I'm sorry. I was just looking at it from that one particular.
No, because we really
Yeah.
need the feedback. Stephanie.
There's some formatting limitations to what we can do on this site presently. You talked about bringing it into your own system. I wanted to point out a feature. Andy, if you'd be willing to scroll to the printer-friendly version, you can do that.
Okay, so one thing I did is I also went to the very top.
You'll find this at what the printer-friendly version button does is
you can do it on a chapter. See, it's down here. I'm sorry, I'm in an activity, and you can do printer-friendly version here. And now I'm in a chapter. Stephanie, is that where you'd like me to do it?
Yes, it doesn't matter where you are. What happens is the printer-friendly button version takes all of the content that is underneath it in that hierarchy. In this case, we took the entire tutorial, and it puts it into a single HTML file for you. And so that is right there, and it's ready to go.
And then you can like print to PDF or print to.
You can just save it as, an entire set of HTML folders with the image assets to work as offline HTML. You can open it up in Word. You could do whatever you want with it from there. So that's just an easy way to get access to it, to import it into whatever tools you would like to use with it.
And one thing I would do though is I would suggest opening it into or pasting it into a Google Doc, because that way you'll be able to preserve the GIF animations. If you paste it into Word, it takes a lot of extra work to reanimate them again.
But if you're saving it in HTML format, it will put all of those associated files into a subfolder, all the images and the other files.
True. And then I'm not sure if there's a trick to opening a saved HTML page, but for example, Stephanie's talking about save as, and you can
open into Word as an HTML also.
Okay. Or hopefully into Google Docs as well.
Whichever. So you have many options. And so I just wanted to show people that option is there for use with whatever tools you'd like to integrate it with.
Yeah, so that's the whole chapter, and we even have all the links listed down here of the associated files.
Yep. Okay, that's all.
Thank you, Stephanie.
Thank you.
All right. So are we okay then to move on from, well, let's see, actually Mark mentioned, all right, so here we are. We're measuring we're twisting the potentiometer back and forth, Cyberscope. So I'm going to twist it all the way clockwise. There's my 10 and change kilo ohms. In a perfect world, it would be right about there. Nope. Can't hold it. Okay, and then at the other end, So it basically goes all the way down to its counterclockwise limit. And for me, it's, you know, anywhere between 10 and 100 or so ohms. And then if I go about halfway, well, guess what? We get roughly half the resistance. And so that's an important thing for the students to experiment with. And so they get to turn the dial like that. And then after turning the dial, we always try to catch the interest with doing something first. And then I leave it up to the teacher to encourage the students to continue into the how it works by assigning essentially homework that we provide. So then we talk about, all right, here's a potentiometer, here's its resistive element underneath. And then this is a little thing called a wiper, which is a piece of metal under the adjustment knob. And it's attached by a hinge right there, and it goes out to the W terminal. So that's how a potentiometer is built. And then we do some examples of, hey, if you turn it, you know, a fifth of the way from counterclockwise limit, you get a fifth of the resistance between W and A, and then the other 4/5 between, I mean, W and B, pardon me, and then the other 4/5 between W and A. And then if you twist it to another position, now you've got a fifth between these two terminals, and then the other 4/5 of 10 kilo ohms between those two terminals. And I really like this ohm meter schematic symbol where it shows the subsystem inside the ohm meter and then your test circuit outside of it. If time permits, it's one of the things on my list to go back and do to the electrical measurements section, because I'm pleased with how that conveys the idea of, you know, that there's a circuit that is the ohm meter and a circuit that you're testing with your ohm meter, since we're building our own ohm meter circuits. And then here is, yes, this, by the way, I'm going to move to the voltage measurements, since the circuit that is typically used is a voltage circuit. So I'll try to come up with something more exciting than potentiometers have different shapes and sizes, but haven't figured out what that is quite yet. So anyway, that's an example of the different elements that are in most of, not every single one, but almost all of the tutorials. Is we have an overview, parts, circuit, script, tests, how it works, try this, did you know, and your turn, and then review and practice with yourself, check, and then half of the available questions, exercises, projects, and their solutions. So that's how that works. Okay, then on to measuring voltage. So for this, what we're going to do is grab two wires. And can you see this okay, or should I zoom in? Okay, I'm seeing one person squinting, so I'm going to try to zoom in a little bit. At least one person, I should say. Too much. Okay, how about that? So we're going to add a black wire from the blue column to J30, and then a red wire from the red column to J28. And in doing so, we are applying 3 volts to the potentiometer. Y'all ready? Okay, excellent. So next up, we're going to, so this is where I have not yet updated it. So this would have a little voltmeter around it, just like the ohm meter from the previous one. So what we're going to do is clip on to the other pair of 3-pin headers. So we're going to disconnect from our ohm meter circuit and then connect to our voltmeter circuit, which is the 3-pin headers on the left that are connected to P0 and P2. Remember, the plastic sleeves can touch each other, but we don't want the metal parts touching each other, because that'll give us bad voltage measurements. Won't hurt anything, but okay. And then after clipping on to those two 3-pin headers, also connect to the H30 with the black probe, and then B29 with the red probe. Okay, everybody ready? Excellent. So, oh, boy, do I wish I'd have just gone straight to this one. All right, everybody, check your connections. So this is the part where we give you and the students a close-up so that you can check and make sure all your little connections are right, because having one of them wrong is something that a student will bring their breadboard to you and ask why it doesn't work. Are we good? Okay. Remember, as always, feel free to unmute yourself if you need a little extra time. Okay, let's see. Trying to think of what's actually different about this particular picture than the previous one. I don't know. Okay, so then we have to do the script, and I'd better take you to a page where we measure volts with the Cyberscope, as opposed to trying to get it out of the, let's see here, script and tests. And then the link to this page. So when you get to this page, right click and save link as the measure volts with Cyberscope. I'll paste that in momentarily. There you go. So that should take you to the page, and then you can right click and download the measure volts with cyberscope.hex. Okay, then we'll go to the Python editor and open up that hex file. Connect, flash, disconnect. Might need to disconnect from the Cyberscope. Connect, flash, disconnect. And then over in the Cyberscope, we'll go ahead and hit connect. And then remember, I left off right at about halfway and it was showing 5 kilo ohms. Well, now it's halfway between 3.3 volts and 0 volts. Which should be, if the display would stay still, it would be 1.65 volts. I'm going to have to look at that because I don't recall the display bouncing around quite so much. And sometimes what happens is either an update I made or an update microbit made can end up causing jumpy measurements. So once you've got this going, what I'd like you to do is try rotating to its counterclockwise limit, then do about 1/3 of the way, which is going to be about 1 volt into its range. And then 2/3 of the way, which might be 1.1 volts and then 2.2 volts, but you don't have to get exactly. Okay, so there's 2/3 of the way, and then all the way to the clockwise limit, and there we are at 3.3 volts. And that is to have students understand that there's a continuum of voltages that they're going to get out of that potentiometer as they're twisting it when it's wired for voltage. Are we good? Shall I move on? Okay. Again, unmute yourself and yell stop at any time, or I have a question at any time. So the next one is designed specifically for students to goof off and have fun, but at the same time, learn how an oscilloscope really works and what it's really for. So we're going to do plot volts with Cyberscope, and I am not sure whether this is going to be, okay, so this is a good one. So this one, we're going to have you download from Google Drive. Okay, here comes a link to the hex file. Download. And so again, it's going to be the same set of steps. Drag and drop the hex into your Python editor, click connect, click flash, click disconnect, and then go over to your Cyberscope. And then start twisting the potentiometer and watch how it responds. Yeah, the way that signal's jumping up and down has me a little bit concerned. I don't know why my voltage would be jumping up and down that much. Of course, it could be something to do with being on Zoom. I'm really not sure. I'm going to look into this because it's important to have it nice and smooth if the measurements are supposed to be nice and smooth. So these little jumping up and downs concern me.
Mine have been smooth the whole time. Like,
okay.
Even when I was checking the voltage before and turning the potentiometer, it would just stay at that spot.
You know,
this is staying. So it
okay,
might be
so that means that I probably have a loose wire or connection somewhere, or maybe even a microbit that's a little bit funny. It's a much older vintage than the ones that you guys have. It was one of the earlier ones to get released. So yeah, I'll have to go culprit hunting after the workshop. But hopefully, I'm glad to hear that yours are not having those little spiky things when they're. Oh, look at that! But it's smooth when I leave it as is. So actually, what that's telling me is maybe my potentiometer has some kind of issue.
Is it maybe
oh wow! Now it all just went away. It's a singing frog.
Was it maybe just not seated in the board well?
Yeah, I pushed in a bunch of wires just now, and I basically pushed down everything I could think of that would, might have gotten shaken loose in transportation, and now it's nice and smooth. Look at that.
Well, this is a good illustration for helping students troubleshoot, at least.
Indeed. Oh, there we go again. And I just let go of the potentiometer when it did that. Yeah, we'll have to look at that. Okay, So this helps explain the voltage over time. Now you can set this to 500 milliseconds and have it be a little bit more responsive with your drawing. And what I'm doing here is I'm kind of summarizing some of the other things that the students will do in the activity. You don't have to do this necessarily. You can also set the trigger. What I did in the Did You Know is actually talked about an engineering adventure I had recently where there was something called a voltage spike that we were seeing coming back from one of our robot motors, basically a test unit that never went into production. And it took a lot of research. So what I just did was I emulated a voltage spike. And there it is. So that's catching something that only happens briefly and every once in a while. So we're waiting, and nothing's happening. And then we'll say, oh, the robot turned and it sent some voltage back down its supply line. And so there was another spike that was even worse than the last one. Oh man, there it is. So so this is an example just of a little real world thing that the students do at the end of the activity. Next up is an angle measurement. And this is where I was hoping that you guys could find some masking tape, because what we're going to do here is turn our potentiometer all the way to its clockwise limit. I say turn to the right to myself, but I don't think that's very helpful. We're going to turn it as far as we can clockwise and then put a little piece of tape on it that's maybe coming, you could, for example, wrap it around and just have a little tag that's pointing to the right, or you could do it, with the cute little arrow like I did in the drawing here. But just a piece of tape to show where you have that basically you've rotated all the way to its clockwise limit, and we're going to call that 0 degrees by putting a little right pointer there. And then we've got our 90, 180, and 270. And then we'll use the script to measure the actual angle that we rotated the potentiometer to. So we should be able to, with the script and knowing that knowing what values we get from an A to D converter that's built into the microbit, pardon me, we should be able to figure that out. So first of all, I'm going to paste in the script for this. Now, this first one is just exposing students to, hey, here are analog measurements with an analog to digital or A to D converter. Okay, so this first one is just the raw analog to digital conversion measurements of pin 4. Now, before this is going to work, I might have gotten a little bit ahead of myself. We have to add a 220 ohm resistor. So I would like everybody to find a red, brown, gold color-coded resistor. And then you can disconnect your probes for now and connect from the row of the W terminal. So row 29, either A, B, C, D, or E. Connect that 220 ohm resistor from that row to row, can't quite read the number, 30, 29, 28, 27, row 26, B, C, D, or E. So right here in the same row as P4, the P4 pin label on your cyber.org Edge IO adapter board. Now for this, we want to disconnect the Cyberscope. So if your Cyberscope is connected, click disconnect. And then I think I pasted in the script already, but let's make sure. Okay, there's the script. And when you run that, we're not going to use the Cyberscope this time. So after you paste in the script, Control A, oopsie, Command A, Command V in the Mac. So we're not going to disconnect either. So we're just going to connect and flash. And let me know when you're all caught up with me. I see one head, at least one head down, a couple thumbs up. Let me paste in the, or I'm going to dwell on the schematic for a little bit again. So again, it's a 220 ohm resistor, red, red, brown, gold. It's going to go from the P4 row to the wiper terminal on the potentiometer. That's row 29. And you can go ahead and disconnect the alligator clip probes. Then copy and paste in the script and hit flash. Okay. Remember, unmute yourself and let me know if you need to go back to anything. Once you've flashed it, this time we're just going to look at the terminal. And notice at the terminal, we're getting a value that says ADC equals, and then a fairly small number for this analog to digital converter. And as I rotate it from all the way clockwise to counterclockwise, not a darn thing is happening for me because I didn't connect my own resistor. There we go. Okay, so I'm going back to clockwise. Now at all the way clockwise, we're actually at almost the maximum measurement. I faked myself out by not having the resistor connected. I was getting low measurements when I should have been getting high measurements. And as you rotate the potentiometer gradually from its clockwise limit to its counterclockwise limit, look what happened. So we have here a range of 0 to roughly 1022. Now, actually, the maximum measurement would be 1023. Including 0, that's a total of 1024 possible measurements. And that is 2 to the 10th, which is a convenient digital value when you're designing little chips to take A to D measurements. Okay, so hopefully, if you're all the way clockwise and you've got that around 1023 A to D measurement, you can put that piece of tape on so that it's pointing to the right. Okay, next up, how do we change that to a meaningful voltage measurement? Okay, so we talk about how an A to D converter works and how it has a bunch of steps, and whatever real value will get rounded down to the next lower step in the A to D value. And then we have a try this, where we're asking you to put your hands on the keyboard as a student and make some adjustments. So I'm going to make those adjustments for you, since time is always of the essence in hour and a half segment. So ADC volts equals ADC, and then we want to print volts. Okay, hopefully I do this right. Okay, did I do it right? Flash, open serial. Yeah, look at that, 3.3 volts when I'm all the way clockwise. And then as I turn gradually counterclockwise, we go down to 0 and then back up to 3.3 volts. How are we doing? You all right? Okay. I see some of you still working on it, so I'm going to give you a little bit more time. Are we there yet, Chris? Not yet. Okay.
Can I see how you modified that code one more time?
Yeah. Oh, I didn't paste it to you. I'm sorry about that. Just a sec. No wonder. Copy. Yeah, so this is part of the step-by-step instructions, but I didn't intend for anybody to have to do those. It was just kind of a demonstration thing. Let's see here. Copy, chat, Command V, there we go. Okay, so there's the actual script in the chat. Okay, so all we did was use, a scalar multiplying by 3.3 volts and dividing by those 1024 possible values. Folks try to tell me it should be 1023, but I'm trying to represent the most common architecture of analog to digital converters. And if you go with that, it's 1024. So that's an important distinction.
Would this work on the microbits 1.5?
Absolutely.
Okay.
All of this should. Now, the thing that did not work that I was talking about before we got started was will work very soon. I just wrote some extravagant code and ran the microbit 1.5 out of memory, but we're supposed to be supporting both, and it's not a problem. I can do this. Okay, how are we doing? Everybody good? Okay, so now we're going to extend that a little bit further to angles, and remind me to paste the code in. So we did one scalar to measure volts, and now we need to come up with some other kind of scalar that when your ADC reads 1023, you get 0 degrees. And when your ADC, that's short for analog to digital converter. And when it's down to 684, we should be at 90, 341, 180, and then 0, 270 degrees. So we're going to scale it so that we get meaningful measurements out of that sensor. And so here we have two ways to do it. So the first way is to use two equations and two unknowns. Now, I don't have the MP4 for this added in yet. So when this gets published, it'll have an MP4 that you can pause and use to lecture the students about how two equations and two unknowns and solving for this problem right here, where you want to have a Y that's in degrees when you have an X that's coming in as ADC values. And so this actually, hello, yeah. Oh, somebody's unmuted and I'm hearing background noise. Just let me know if you have any question. So this goes through the math of the solution. But at this point, there's another way which is to use a function. So since this is the draft, the solution is actually in here. This is one where the students are going to have to figure it out, or do the code themselves. They'll have the equation of y, m, x, and b, but they'll have to actually modify the code themselves. Now, another thing that I did was, this is, I believe, the third or fourth time that we've solved with y equals mx plus b. So it's time to move on from that. And it's time to actually show that, hey, you can just add a function that does the entire y equals mx plus b calculation for you. And you just say, here's the value I've got, and the start and end ranges of what those values could be. And then we want to convert to angular ranges. And so, for example, 1023 was the start, 0 was the end on our input, ADC value was the measurement. Then 0 degrees is when you're at 1023, and 270 is when you're at ADC of 0. And so basically, it's just one call to map, and it saves you having to do 2 equations and 2 unknowns. So what the your turn actually might do, because I was thinking that some of these may be slightly high hurdles, what the your turn might actually do is it might say, compare and contrast these 2 code examples that you got to see in the did you know. So I'm pasting the first one in, and let's verify that it gives us 0 to 270 as we go from clockwise to counterclockwise limits. Chat, paste, whoops, paste. Okay, so that's one way of doing it. Oh, that's interesting. I have an error. So there's 270, that's correct. But
Same
that
error.
should be 0. So what did I do wrong here? Angle. Let's try that. Okay, now I'm all the way clockwise. I've got about 0 degrees. Yeah, there's 90. Okay, let me paste this corrected one in. Okay, here comes the corrected version. There we go. All right, that should give you much better measurements. Okay, how are we doing? Have you got that now? Is that good? Excellent. So now we have something that's a real sensor. Now, I'll go ahead and paste in, fingers crossed that it works, the other adaptation, which uses the map function, which essentially anybody who's working in the field, if they're solving for y equals mx plus b when they could be using a map function, they may get demerits. So we really want to use the map function at some point so that folks know both approaches. Here comes the map function version of the script. By the way, map is built into, map first made it into kind of an official API, so to speak, for the microcontroller world and the Arduino when they came out with their language. They have a map and a couple of other nice math shortcuts. Yep. Still working. Oh, looking really nice. Okay. Yeah, so the map one works as written. Okay, how are we doing? Good, good. Okay, if anybody who's not in my little grid of attendees is having trouble, just shout out. Hold on for a minute. Okay, so let's see, we are running a little low on time now. But then again, potentiometer controlled light is a quick little one anyway. Copy. Okay, there is potentiometer controlled light. Go ahead and try it out. Close serial. Select all. Paste. Flash. You don't even need to open serial for this one. It's just a matter of monitoring the light as you turn the potentiometer. So, so there it is all the way in one direction. And then as I gradually turn it to the other limit, it's all the way bright. So in this case, we're mapping the ADC in to the, or A to D in to the D to A out. And it's a very simple map because they both have the same number of increments, that being 0 to 1024. Looking good, Aristides. Nice.
I only had an issue when you started working with the pot. I had a pot, well, I lost my parts, the kit with parts.
Oh,
so it's a scavenge. I was getting parts from different older kits, and I had a logarithmic potentiometer. So,
oh, really?
Yes. So I was not getting much farther. So I got a really, really old kit that I knew I had a linear one, and now I'm good.
Yeah, that logarithmic potentiometer, I would imagine that it kind of really jumps, doesn't it? Okay. So the next one is going to be kind of fun, and for it, we'll need to connect our servo batteries. Let's see here. So, and lo and behold, look, we have a corrected red wire on the left. Yay! So now I just have to go back and delete it in all the old drawings and redo those too. Fortunately, there aren't too many servo drawings. If it was something that went all the way back to the very beginning, that would have been a big redo. Okay, so plug in your battery, make sure your servo is plugged in. Can I get some directional thumbs on how you're doing? 1 up, 2 up, 3. All right. So, so now we're going to use the potentiometer. And in this case, this script I'll be replacing with one that uses the mapping function. I think I may have done enough 2 equations and 2 unknowns already, although I'm open to correction on that. Bear with me. Okay, I need to get back to the chat. Paste. Okay, so here is the potentiometer controlled servo. Oh, you know what? I meant to have us all set up our servos so that they were 0 to 180. Let me know if you have any trouble doing that, and we can do that. But here I am twisting the potentiometer in the bottom of my screen, and you can see that the servo is turning on the top. And the interesting thing is that right now, the direction I turn the potentiometer is the opposite of the direction that the servo turns. And so it's left to the students to correct that by using a negative sign and some other math possibly. I need to take a look at the tutorial. Share screen. Oh, by the way, was that, were you able to see that on my screen? Okay, good, good. And hopefully you're doing it for yourselves as well. So I'd like to point out that we started with lights, and then we did push buttons, and then we did a servo. So by this point with the potentiometer, we have 2 output devices to play with, the lights and the servo. And notice that there's kind of a mix and match thing going on. And that's a really important exercise that we do repeatedly so that students get the idea of integrating more than one subsystem into their application code, firmware, whatever you want to call it, that they're writing for their microcontroller into their scripts. Okay, so have we all got twisting control over the potentiometer or over the servo? What do you think? Is that cool? Okay, well, here's another one from the servo chapter. So I need to go back to learn.parallax.com. And to this, well, I probably could have followed the slide, but I mentioned that so at this point we have 2 input devices, those being the push buttons and the potentiometer, but there are input devices built into the microbit as well. So what this application is doing is if you hold the servo against the microbit edge adapter like that, you'll see that both the little display on the microbit and the horn on the servo try to point up the whole time. Now, depending on how the horn on your servo is mounted, it may not point up, but it should it should work pretty nicely for you. So here is accelerometer points up on its way into your chat. Okay, it's in the chat. Select all, paste, flash. Okay, so for this one, you're going to have to hold the board up like it's a steering wheel. So I've just about got it set here. Okay, stop share. Okay, so if you've got the servo horn set, it should be apparent that both the LED display and the servo horn always point up as you hold your board vertically and rotate it. Do you see how both the little clock needle and the servo are both pointing upward as I hold it vertically and rotate it? Is that visible in the screen? And would anybody like help getting their servo so that the horn is properly tracking the up direction? What I'm going to do is I'll show you that. It is in the book. If you want your horn, the servo horn, in the proper direction, go ahead and pull one of the batteries out of the battery pack to stop power to the servo. This is only if you need to adjust your servo horn. Okay, then the next thing to do is going to be take the servo here, and just a sec, I need to get it. So, okay, so rotate it all the way to its clockwise limit. Now, you might have some unusual position. So it might be like this, and you finally find your clockwise limit. Well, once you've found your clockwise limit, then remove the horn and put it back on like that, pointing to the right. Then you can put the battery back in, and if you hold the servo against the board like I did, you can expect to have the servo horn pointing upward as you rotate it in a 180-degree range. So when your USB cable is pointing straight up, that's going to be 90 degrees. Looking good. Oh yeah, I like that, Ari. That looks fantastic. Okay, so a quick heads up, there's a lot of, it's not really a quick heads up, it's just kind of more of a footnote. There is quite a bit of material on this. So there's a before you start section. Frequently it's up top here at the chapter introduction, but we have a before you start at the activity level. And there's some cybersecurity introductions that—
I can't see your screen.
Oh, thank you. I did it again. Share screen 2. There we go. Okay, so here we are. We're in servo position control right now, and we're at the servo tilt control. Now, I just did something from the script and tests, but backing up just a little bit to the intro for this, there's a before you start section. And there are 3 tutorials that can be followed for a more in-depth look at how the built-in accelerometer inside the microbit works, and understanding how tilt and measured angle can be calculated with your microbit. So these are microbit only activities, but they work great, and there's a lot of good information in there. And especially if one of your goals is to talk about trigonometry and get your students to appreciate trigonometry and angular measurements and the cosine and arc cosine and arc sine functions, this is a really good additional lesson. And with that concludes our application presentation. And I have just a few final things to show you. But before that, did everybody get that to work? Awesome. I'm getting a kind of from Elaine. If you want to stay after or do a Zoom meeting afterward, at some other time, we can get you running on that.
It's been good until now. It's kind of possessed a little and just moves on its own.
Well, when you have it sitting flat, it will move on its own.
Oh, okay.
As you hold it vertically.
Oh, okay. That's what made the difference.
Yeah. Now you can actually just kind of tilt it up. If you tilt the USB cable up a little ways, that should be enough to get you to a particular direction. But ideally, you want to point the USB cable straight up and then rotate, hold your board vertically. Oh, beautiful. That was an easy tech support solution. All right. So the last things I had in mind to talk about today are, first of all, what we have planned versus what has been completed. And I am screen sharing. Am I sharing the right screen?
Mm-hmm.
Okay, so everybody sees a lesson roadmap? Okay, excellent. So, so everything that is a turquoise link is published to the web. So this yellow one right here is the potentiometer draft that we went spelunking in today. The heavy duty electronics lessons, or the remaining in-depth lessons after the potentiometer that I had planned, were things like tones, which are sine waves, and music, more generally AC signals. So when you see those exponential decay graphs, there are parts that, when put together, create those. And then I also wanted to do a little bit about signals and how filters work. So that was one thing. Those were the two more substantial chapters. And then after that, just a lot of fun, short, here, try this kind of thing. Try a light sensor, try a multicolor LED. Yeah, there will be several things to do with it, but it's not going to be as in-depth and using math and et cetera as this. These are just kind of, you did a lot of work. And so now here's some fun icing on the cake. And if there's anything that's of particular interest to you, let me know, because if we need to pause writing development, I want to make sure to get the most important thing in. Do you think that's the icing on the cake, or do you think that's the AC signals type stuff? Do I have any thoughts from our audience here? And we'd also want to talk with reference to what you're teaching, whether either one of those matters more than the other. My guess would be, of course, that for middle school, just having lots of fun circuits to build and things to try is going to be important, because they're not going to be digging into sine waves and exponential decays and filters. These are the more math intensive ones, whereas these are the fun ones. Any opinions? I guess I should mention that my personal interest is very much in these. but I believe that after the potentiometer chapter, that it would be more prudent to start posting some fun applications with new circuits that are shorter and sweeter. So that's the current plan. Does anybody have additional thoughts on that? Shall I just take silence as assent?
Yeah, I like the idea of several fun activities to do.
Okay.
Thinking about using these with a summer camp with middle school kids. So
Yes.
fun things they could do would be beneficial for me personally.
Yeah, well, the thing that's most beneficial for me is having it be useful for you, because that way I might actually get the permission to do the sine waves and the filters and stuff like that. But it's got to be selling like gangbusters first. Rebecca?
I was going to say, because I do have cyberbots in my classroom, and I think this is a nice tie into that. And I was going to say I could see my 7th hour really liking music, because most of those kids leave my class and go to band.
Oh, yes. Yeah, music is tremendously popular. I would say that in addition to video games and robots, that music is the other next thing. So yes, music is only supported currently. Oh, interesting. You have cyberbots, so you could actually borrow the piezo speakers off the cyberbots if you have microbit 1.0s. You could also borrow the microbits from the cyberbots. And oh, I'm getting ahead of myself. Okay.
Yeah, I was going to say, you said you were going to talk about that, and I was like, that's definitely what I'm going to be perking up, because I have a lot of pieces.
Okay, well, purchasing tips then. Number one is www.parallax.com is where you would go to buy kits. Number two, there's a cool little, you can hit shop and then select microbit, and it takes you here. And I'll just cheat and do a shortcut to it, which is in the slide. So you can also get here from the slide. Command scroll wheel, no. Control scroll wheel, nope. Control plus, command plus. There we go. I'm not very Mac literate. So this shows all the microbit kits that you could conceivably get. And so it came to mind that since you have a fleet of cyberbots already, that means you have a whole bunch of microbits. And so money saving wise, we have this kit that comes without the microbit, and you can save about $20 on the kit because you already have your microbit. So if you have it set up in a way where you can reasonably switch between cyberbots and the electronics kits, then this would be a great option. Other options include, this is the complete set. So this has the microbit in it, and it's a little higher in price. And then, oh, this is an important one. It's the small parts. They will get lost.
That's the one I lost.
Yeah. And ended up with a logarithmic potentiometer.
Yep.
You know, I've never played with one of those. Oops.
It's usually only useful for volume, for sound systems.
Yep, that does make sense. Paste, let's try that. Oh man, let's see, copy link. I've got to copy the link. Copy. Try this. Paste. Okay, there you go. So, so this is an important one because you can use it to replenish small parts that get lost or broken. And it's also not particularly expensive. If you get a couple of these in addition to any group of kits you order, it'll definitely help on the small part replacements. The student resources for this are primarily at learn.parallax.com. And then when you go there, there'll be a what's a microcontroller for the microbit link. right here. And just as a reminder, this is your textbook for this kit. Each one of these is a chapter. And we'll add some projects. That's what the there will be a project section below this with the multicolor LED and things like that. Now there's also teaching resources. Oh, I'm sorry, that's right. This is a page that I forgot to mention early. It's so you tried out one set of Python tutorials for the microbit that are on the Learn site. This is at the microbit well, it's readthedocs.io, and it's microbit's official documentation for Python with the microbit. So this would be microbit only things where you can try, and there's a lot of really fun stuff here. Couple examples would be, where's the compass? Here it is. Compass is a must try. Got a little bit of example code right here that you can try. And, you know, it gives you a compass heading on the little display. Lots of fun things to try that are explained as you go in this tutorial. If you need additional material or want to approach it from a little lower level first, that's another option. This is a repeat of an earlier slide. This is microbit.org, make it code it. And so they have over 100 examples that you can try out. And then I think there's like 80-ish if you filter down for Python. And then there's a lot more material like that and additional curriculum. And this is also a repeat. These are the YouTube links of the Granite School District workshop. It's definitely worth a watch if you need additional material that comes before either the Cyberbot or the electronics kit, just using the microbit on its own. Okay, here is the Educators links. I apologize, I took us a little over without realizing it. I will wrap this very quickly. So learn.parallax.com, you can just click the Educators link here. And then this is where all our teacher materials are. Now, you can't get to all of it. You can get to lots of it, like the tutorials of, you know, there's lots of helpful links here, but the Educator material is locked off. However, once you follow the log on link, I'm using my personal account as opposed to my web developer account. Let's see here. Not a hackable password. Okay, so once we're in, you can go back to the Learn site and should be able to refresh. Okay, so now there's no closed lock anymore. As a teacher, this is what you'd see. The assessment materials. And you can follow this link, and what you'll have is, for each chapter, a test bank. Let me go to something in the middle to make sure I get a generalized version. LED lights. You're going to have the teacher's guide, the test bank. That's the second half of the solved questions, exercises, and projects. And then a worksheet that an educator has made. And Stephanie, would you say that that's at middle school level, those worksheets typically? You're muted, sorry. Uh-oh. Well, we can't hear you, although oh, there we go.
Yeah, I'm not entirely sure. I think it could be adapted up or down depending on how much of it was there.
That's a good point, because the test bank can even go into, say, your technician school or engineering school, depending on what portions of it you use, whereas the worksheet seemed a little lighter to me. And then the teacher's guide is a teacher's approach to, you know, it's got all the teacher's guide materials that as a you know, having had my training in electronics, I'm not as familiar with how to do this, but Nicole Litterer, our person who does this, does a nice job of including stuff like the core concepts and the applicable standards for your, if you need to get some grant money for it. And then just kind of in a nutshell explanation of how to, you know, go along and teach this particular chapter. So those are things that you'll find once you have logged into the learn.parallax.com site. So that was that piece of homework that I mentioned earlier, where you want to have a password to the Learn site. So when you try to find your assessment materials, you'll need to be logged in using that password you created, or just, you know, your ability to log into the learn.parallax.com site. Okay, last but not least, something, or oh yeah, that's right. There was cyber.org. If you're a teacher in the United States, they have some microbit curriculum as well. And then also microbit.org has lots of microbit curriculum. So again, lots of things, lots of material that can be filled in ahead of either the Cyberbot or the What's a Microcontroller kit. On the subject of the Cyberbot, you can unplug your microbit from the What's a Microcontroller kit, plug it into your Cyberbot. And the Cyberbot has a propeller microcontroller underneath this black board right here. And the microbit actually talks back and forth with that other microcontroller. That other microcontroller takes care of a lot of the robotic stuff. And there's some great lessons that are in there. One example would be just repetitive loops. Okay, here we have one go forward and turn right and then stop maneuver. Well, if you take that maneuver and put it in a loop, guess what? You've got a square. The robot does 4 go forward and turn right maneuvers because you took the one routine and stuck it into a 4Y in range, you know, 4 variable in range loop. And so we went from go forward and turn right. Yeah, that is right. To go forward and turn right 4 times to draw a square. The Cyberbot has lots of great stuff. Like here's an example where it's got whisker touch sensors, so it can bump into stuff and find its way like that. It also has light sensors where you can shine a flashlight and it'll follow the flashlight that you shine. Run that one more time. Flashlight on, starts to turn and follow. There are also infrared sensors. These are kind of like the whiskers, but they're the non-contact version where it can detect the obstacle ahead of time. And it's actually just a slight modification to the whiskers code. It behaved as though it had bumped into the box, even though it was a few inches away. Now, what's really neat about the microbit is it has built-in radios. And so this is an example where, wow, I can really hear the CPU fan on my computer going. This is an example where we have one microbit. Microbits have built-in radios. So we've got one microbit connected to a computer here, and we're using the terminal to send our commands to this microbit. This microbit forwards it over radio, over its built-in radio to the built-in radios on all the microbits on all these robots. And the effect is pretty awesome. So you type in the speed and the duration of each maneuver, and there they went forward and backward and turned right for several revolutions, back up, pivot on one wheel, turn left, back up, pivot on another wheel again. So that's some cool stuff. We have an educator hotline, 24/7, right, Ari? He just picked up the phone. And
yeah, I'm right here.
Yep.
Ready.
And so, but he might be attending a workshop. And Ari, would you put us on hold to grab the call, or would you stick with the workshop? I know that's a
I will
difficult
put you on
question.
hold. Yeah.
Yeah.
hold.
You'd put us on hold and talk to the teacher. All right, then. So some of the Cyberscope funding and other tutorial funding came from cyber.org. So we'd like to thank you all at cyber.org for that. And thank you everyone for coming from Parallax. And that concludes today's workshop. Stephanie, would you like to stop? Or actually, we can have some discussion, I guess, since some of you are still here. Any final comments or questions before we sign off? Yes, Mark.
With whiskers and chasing a light, I feel like you've invented a cat.
More than that, we've invented a cat toy.
Yes.
I've been developing and testing those applications since the early 2000s, and our cats have always been somewhere between bewildered and stern with the robots.
Yeah, we just need to put some googly eyes on that thing. I think we'll be all
Yes.
right. I did have some feedback, but I can wait until after you're done recording.
Okay.
I will just pop in really quick and say that I am sending out participation certificates with 8 hours of time spent to all of you today. So thank you very much. It also has the emails and phone numbers that Andy was just mentioning that you might find useful.
Oh, good.
Okay.
So that'll include this OMI. Yeah.
Okay, with that, I will stop the recording then.
Okay. Thanks for coming, everyone.